Swayam Prabha. Digital India. Educated India.
Last few classes, so we have started looking at the statistics of various particles depending upon whether they are distinguishable or indistinguishable, and we saw that all the classical particles can be treated as distinguishable because their de Broglie wavelength is much smaller than their size. So we can, in theory, we can track them. However, there are quantum particles which are very small, and upon collision there is uncertainty where they go after collision. So we lose track of them and we call them indistinguishable particles, right. And on top of that, we also classified quantum particles into two depending upon what spin they have, right. So integer spin particles we called them as bosons, and half integer spin particles we called them as fermions. So essentially what we have done so far is, so we have looked at what's known as Maxwell-Boltzmann statistics, Fermi-Dirac statistics, and Bose-Einstein statistics. And Maxwell-Boltzmann statistics is shown by particles which are distinguishable, and they show classical statistics. So these are classical particles. So however, Fermi-Dirac statistics is shown by indistinguishable, and they are quantum, and they are also fermions, so half integer spins, right. So half integer spins. Similarly, bosons are also indistinguishable, right. So these are bosons and they have integer spins, right. So these are also quantum particles. So this is also quantum. These are also quantum particles. And the result that we have seen so far is that the occupation index, which we have been denoting as Ni by Gi, right. So in this case it comes out to be e raised to the power alpha plus beta epsilon I for fermions. So maybe we can call it MB. So for fermions, the distribution Fermi-Dirac, which is again Ni by Gi, the occupation index, that takes a slightly different form, e raised to the power alpha plus beta epsilon I plus 1. And for bosons, so this is Bose-Einstein statistics. So the occupation index, that becomes e raised to the power alpha plus beta epsilon I minus 1, right. And these three expressions, they look very similar to each other, except there are terms in the denominator which are different. For example, there is a plus 1 in Fermi-Dirac, in minus 1 in Bose-Einstein, and there is nothing in Maxwell-Boltzmann. And we will see down the line how these factors, they make huge they have huge impact on the properties of systems, that depending upon which particles they which class they belong to, all right. And also in the last class, and also here alpha and beta are unknown, so they were Lagrange multipliers which we used to solve the equations. And in the last class we in fact saw that beta is essentially 1 divided by kBt. So this we have already derived in the last class, and today what we will do is we will basically evaluate. So evaluate the alpha, right. So what is alpha? So this is what we will do today, right. Okay, so if you remember, so in the last class, right, so we basically stumbled upon an equation which was the expression for entropy, which was as follows. So entropy was n times Kb times log z, plus beta times Kb times u. Okay. So, this was one of the equations that we had in the last class, and since now we know that beta is 1 by Kbt, so this implies I can rewrite my entropy as NKB log Z plus beta plus so I will just substitute for beta as 1 by Kbt. So, this will just become u divided by T. Okay. So, now okay, so let us now use the definition of Helmholtz potential, right. So, Helmholtz potential, which is F, right. So, this is given by u minus Ts, right, and what we will do is we will essentially substitute for the value of entropy in that equation, right. So, I will just substitute S as NKB log of Z plus u by T. Okay. So, if I do that, so I get F equals u minus T times NKB log Z plus u divided by T, and this essentially becomes u minus NKBT log Z plus u, right. So, this cancels out, sorry, this will be minus. So, this is minus. So, this cancels out. So, u cancels out. So, we are left with minus NKB T log Z, and this is the Helmholtz potential. Okay. All right. So, but we also know, okay, so since F is u minus Ts, right. So, we can also write, so dF is du minus Tds minus SDT, and we know du is Tds minus Pdv plus mu dn minus Tds minus SDT. So, few terms cancel out, and this becomes minus Pdv plus mu dn minus SDT. So, from here we know that mu is essentially the partial derivative of Helmholtz potential with respect to number of particles n evaluated at constant volume and constant temperature. All right. Basically what we will do is, so this is the chemical potential, and we will now substitute the value of F here. So, this is essentially partial derivative with respect to n of minus NKBT log of Z, and this simply becomes minus KBT log of Z, and this is the chemical potential. So, this is the chemical potential. All right. Okay. And again another equation, the result that we saw in the last class, you have to check your notes. So, we also saw, so from previous class, okay. So, we also saw that e raised to the power minus alpha was essentially n divided by Z. Okay. So, which implies I can just write my minus alpha as log of n minus log of Z. So, I have just taken log on both sides, and from here I can write my alpha as log Z minus log n. Okay. So, and what I will now do is I will substitute for log Z from this equation. So, log Z is basically minus mu divided by Kbt. So, I will substitute it here. So, that implies my alpha is basically minus mu divided by Kbt, right, minus log of n. Okay. Or what I can also write is my mu divided by Kbt, if I take it to the other side. So, this is minus alpha minus log n. Okay. And again I want you to pay attention here, right. So, what we are interested in is, we are interested in evaluating the this quantity alpha, which is a constant, right. But we also know, so in our system, so since n is conserved, right. So, total number of particles in our system is conserved, which implies log n is another constant. Okay. So, we can very easily just redefine our alpha to be as alpha plus log n, right. So, we can always since we are just adding or subtracting a constant. So, therefore, we can define our alpha. So, redefine our alpha or minus alpha as minus alpha minus log n. So, therefore, the final result that we have is, so our alpha is basically nothing but negative of chemical potential divided by kBt, okay, and this is our second Lagrange multiplier, okay. We already know our first Lagrange, or in fact this was our first Lagrange multiplier, and we already derived our second Lagrange multiplier to be inverse of kBt, okay. So, therefore, our complete derivation is complete, right, and now using this I can finally write down the three statistics that we have seen. So, Maxwell-Boltzmann, okay. So, basically what I am doing is I am just going to substitute for alpha and beta in these equations, okay. So, my f of mb takes a form, okay. So, what I am now going to do is, so remember in in all our statistics there is a recurrent quantity which is alpha plus beta epsilon I, right. So, I can write my alpha plus beta I, that becomes minus mu by kBt plus 1 by kBt times epsilon, or I can just rewrite it as epsilon minus mu divided by kBt, okay. So, therefore, I can rewrite my final statistics as follows. So, Maxwell-Boltzmann statistics becomes e raised to the power 1 divided by e raised to the power epsilon minus mu by kBt. The Fermi-Dirac becomes 1 divided by e raised to the power epsilon minus mu by kBt plus 1, and Bose-Einstein statistics takes the form 1 divided by e raised to the power epsilon minus mu by kBt minus 1, okay. So, this is our final result. So, this is the occupation indices for three statistics: Maxwell-Boltzmann, which is classical and distinguishable; Fermi-Dirac, which is indistinguishable fermions with the half integer spins, and these are quantum particles which are again indistinguishable, but they have integer spin. So, they do not obey Pauli's exclusion principle, okay. So, before I start discussing the differences between these three, so let us now, like I promised, so let us now fix the problem that we had with the partition function of the ideal gas, right. So, remember when we were looking at, when we were deriving the value, so remember when we were looking at the partition function of the ideal gas, so we made a drastic assumption that evaluation of the partition function we can just sum over energy states of single gas molecules and just raise that value to be raised to the power n, right. So, remember what we did, okay. Okay, so before I basically start discussing these in detail, so let us now correct for the ideal gas partition function, all right. So, correcting the ideal gas partition function, okay. So, I will recap a little quickly what was the problem that we had before. So, earlier we basically we claimed that the partition function of an ideal gas, which is essentially sum over energy states, right. So, sum over e raised to the power minus beta E, where the sum over energy states is for all states, so states of all molecules. Okay. So, this is what by definition it should be, but we made an assumption that rather than summing over all the states of all gas molecules, we can just evaluate this sum over states of a single gas molecule. So, states of single molecule, and we can just raise it to the power n. So, where epsilon is the average kinetic energy of single gas molecule. All right. But we saw that when we make this assumption, right. So, when we just raise it to the power n, So, we are inherently assuming that all the gas molecules, they are distinguishable, right. So, we can distinguish between all the gas molecules are carrying certain tag. So, the total number of states is essentially the number of states raised to the power those number of particles. Okay. But it turns out, so when we proceeded with this approximation, so we derived the quantities like entropy, which we ran into trouble because that entropy was not really defined at t equal to 0, and also we ran into a paradox which is known as Gibbs paradox, where we saw that if we look at an ideal gas in equilibrium, right, the entropy change in equilibrium was non-zero. Okay. So, it should be non-zero, because if you have a system at equilibrium, it is a reversible process, all the processes happening in an equilibrium state are reversible. So, they should not ideally lead to any entropy change, right, but we were getting a finite entropy change. And moreover, we saw that the free energy, the Helmholtz free energy was not really extensive. So, it was not scaling with the number of particles in the right way. Okay. So, we ran into all those troubles. So, then I kind of promised that we will come back and correct it, and that is exactly what we will do, right. So, basically what is happening here is, so here we assumed, right, in this assumption, so here we assumed gas molecules to be distinguishable and classical, right. So, this is still a classical problem, but we will see whether we can correct these problems if we assume these gas particles to be indistinguishable, right. So, now the situation is such that what I am doing is I am not changing the gas, the molecules are still moving around, these are ideal gas molecules, but earlier in this assumption we assumed that all the gas molecules, they are carrying certain tag, and that tag remains with the gas molecule. But now let us assume that tag does not exist. So, in the sense, if I have particle number 1 and molecule number 1 and molecule number 10 in this room, if I interchange their tags, and you can very well imagine see that the state of the system will not change, right. So, thermodynamic property of this gas in this room does not depend upon which tag each and every molecule is carrying, right. We do not really have to worry about it. So, in some sense we were over calculating the number of states while calculating the partition function in this way. Okay. So, what we will do is we will remove this condition of distinguishability, and we will assume, so from now on for correction, so to correct it, okay, to correct it, we relax the condition of distinguishability. Okay. And we assume that the gas molecules are indistinguishable. Okay. And for that, what we have to do is we just have to divide this number with n factorial. Okay. So, if we divide it by n factorial, that means the particles are indistinguishable. Okay. So, therefore, the corrected partition function, okay, so the corrected partition function goes as follows. So, Z corrected is basically Z, this Z divided by n factorial. Okay. So, this is essentially 1 divided by n factorial times sum over e raised to the power minus beta epsilon, and now this sum is again over energy states of single molecule. I will just mention single molecule raised to the power n. Okay. And from the previous classes we saw that the quantity in parenthesis is basically this. Okay. So, this was V divided by h cube times 2 pi m kBt raised to the power 3 by 2, and this entire thing raised to the power n. Okay. And now let us try to simplify this. So, from Stirling's approximation, right. So, from Stirling's formula, n factorial is n raised to the power n e raised to the power minus n, right. So, this is the n for large n, right. Okay. So, if we substitute that there, so we can write our corrected partition function as follows. So, this simply becomes v raised to v divided by n h cube, right. So, I am absorbing n raised to the power n inside times 2 pi m k b t raised to the power 3 by 2 and divided by e. So, this exponential and this entire thing raised to the power n, and this is the right form of the ideal gas partition function, right. So, ideal gas partition function with considering the molecules are indistinguishable, right, with indistinguishable gas molecules. Okay. So, this is essentially the classical indistinguishable partition function for an ideal gas. Okay. Okay. So, now that we have the partition function, now we can derive all other thermodynamic quantities. So, let us start with Helmholtz function, right. So, Helmholtz function, Helmholtz potential, right, and the corrected Helmholtz potential I am just denoting it by Fc, that takes the form minus kBt times log of Zc. Okay. And if we do that, if I take log of this, this simply becomes, maybe I can write it on the next page. So, this becomes minus n kBt times log of v divided by n h cubed times 2 pi m kBt raised to the power 3 by 2, and there is another e in the denominator. Okay. So, this is t. Okay. And now we can see that we have removed that problem that we had before, right. So, now if I, so this is corrected Helmholtz potential. Now, clearly if n goes to 2n, right, what happens to this Fc, right. So, this Fc becomes, so if I substitute, this becomes minus 2n kBt times, so if I take n to 2n, my volume will also double, right. So, V goes to 2V because it is an extensive quantity, and there is 2n h cubed times 2 pi m kBt divided by e raised to the power 3 by 2. Okay. And you can see that this cancels out and there is a 2. So, this just becomes 2 times Fc, right. Okay. So, this is this is Fc with 2n number of particles, and this is the original Fc with n number of particles, right, which implies Fc is truly extensive, right. If you remember earlier, we saw that there was n missing here in the denominator. So, therefore, this was not really coming out to be twice the old value of Fc, right. So, therefore, by considering the ideal gas molecules to be indistinguishable, there is another factor of n which appears in the denominator, and our Helmholtz function becomes truly extensive. Okay. So, one problem is solved. Okay. And similarly, now I can also derive the entropy from the partition function or from the Helmholtz function, right. So, the entropy, the corrected entropy is negative of partial derivative of corrected Helmholtz function with respect to temperature at constant number of particles and volume. And if I basically just take the derivative of this, okay, so this becomes, so minus will disappear. So, this becomes kb, and I am first taking the derivative of this term. So, t goes away. So, this is log v divided by n h cubed times 2 pi m kBt 3 by 2 divided by e, and now I am going to take the derivative of the t which appears inside this log, and I will use the same old trick. So, I will just separate log of t raised to the power 3 by 2 and all other terms which do not contain the temperature, right, and that log of t by 2 will give me the value 3 by 2 t, right. So, this becomes so there is the second term basically becomes plus kb n t times So basically del by del T. So I am separating that del by del T of log of T raised to the power 3 by 2 plus partial derivative of all the other terms which do not have temperature. So V divided by NH cube E times 2 pi m kb raised to the power 3 by 2, right. And you can see the derivative, partial derivative with respect to T is 0 here because there is no temperature term, and this simply becomes 3 by 2 times 1 by T, right. So finally I can write my corrected entropy as follows. So this is N kb log of V by NH cube times E times 2 pi m kbt raised to the power 3 by 2 plus 3 by 2 n kb. Okay. So this is the second term. So this 3 by 2 and T cancels out, so n kb, and this is the correct form of the entropy of an ideal gas, where the gas molecules are now classical but indistinguishable, right. So and this equation has a name, so this is known as Sackur-Tetrode equation. Okay. So this is the corrected form of ideal gas entropy. And again let us look at the earlier paradox that we had, that the entropy of ideal gas in equilibrium was non-zero. Okay. So let us see if that problem is solved. Okay. So let us now see the entropy of mixing. Okay. So basically we are solving that paradox, it is known as Gibbs paradox. Okay. So essentially the way we framed that problem was as follows. So we had an ideal gas in equilibrium, right. So it had n number of gas molecules and it is isolated, its volume remains fixed and so on. It can't exchange energy, it can't exchange number of particles, and the walls are rigid. Okay. So and originally it has n number of particles, the volume is V and the temperature is T, and let's assume that the mass of every molecule is m. Okay. And what we are going to do is we are going to put a wall here, so that we divide our system into exactly two parts. So with half the number of molecules on one side occupying half the volume, and the temperature is T, and similarly in the other half we have n by 2 number of particles, V by 2 volume and temperature T. Okay. And our aim is now to okay, so since we have divided it with the wall, and our aim is now to remove this wall immediately and see what is the change in entropy. All right. So now we can see that the initial entropy of this configuration, okay, so initial entropy, so let us call it SI, which is S1 plus S2, so sum of two subsystems, and both the subsystems have n divided by 2 number of particles, the volume is also V divided by 2, and they are at constant temperature. So we will basically substitute these values here. Okay. So this basically becomes using this equation, Sackur-Tetrode equation. So this is n by 2 kb log of V by 2 divided by n by 2 h cube E times 2 pi m. So mass of molecule is m, kBT, T is the temperature, plus 3 by 2 times n by 2 kb. This is for the subsystem 1, and you can check, since the quantities are same on the other subsystem, it is the same thing. Okay. So same as before, and this just basically becomes 2 times this quantity, right. And this you can, if you multiply by 2, this just becomes, so n times kb log, so n by V by 2 by n by 2 again gives you V by n h cube E times 2 pi m kBT raised to the power 3 by 2 plus, so if I multiply this by 2, so this becomes 3 by 2 n kb. Okay. So this is the initial entropy, and now you can, now the final state is where we just remove this partition. Okay. So we just get rid of this partition, And now what is the system we have? We have a system with n plus 2 plus n plus 2 particles, which is n particles, which is occupying volume V, and the temperature does not change, right. And you can very easily check that the final entropy will also have the same form, okay. And this basically implies that SF minus SI is 0 as expected, okay. So, essentially what we do in this thought experiment is we basically introduce a hypothetical wall in an equilibrium state where the number of particles and the volume and the temperature is same on both sides, okay. So, we never really change the system from its equilibrium state. So, therefore, we do not expect any entropy change. But if you remember earlier, when we did not have this n factorial or n factor in the partition function, we were not getting it as 0, okay. So, we got rather we got so we got, maybe I can write it in red. So, we got 2 times n kb log 2 with the old partition function, okay, where we assumed the gas molecules to be distinguishable, all right. So, therefore, this is if we consider the gas molecules to be indistinguishable, we solve the Gibbs paradox, okay. Okay, so, now let us go back to the results that we obtained. So, basically the Maxwell-Boltzmann, Fermi-Dirac and Bose-Einstein statistics, all right. So, now let us basically stare at them little bit more, okay. Okay, so back to classical and quantum statistics. Okay. So, the first one that we had was Maxwell-Boltzmann, okay. So, there we saw that the occupation index FMB is essentially 1 divided by e raised to the power epsilon minus mu divided by kBT, okay. And let us now let us look at this distribution closely, okay. If I plot this f as a function of energy, okay. So, there is this mu chemical potential somewhere here, okay. Now, you can very easily see that okay. So, basically you are going to plot this, right. So, we can see for epsilon equals mu, right. So, this becomes 0. So, f of mb is 1, okay. So, we know that at epsilon equal to 0, so this value is 1, okay. So, this line has to pass through this, okay. But we also see that for epsilon much greater than mu, okay. So, if I take epsilon to be much greater than mu, so denominator is much bigger. So, my f of mb is much smaller than 1, and similarly for epsilon less than mu, right, my f of mb becomes greater than 1, okay. So, this is a function which passes through 1 at mu and which becomes greater than 1 as epsilon is less than mu and becomes much smaller than 1 when epsilon is much greater than mu. So, if I can try to plot it, so this looks something like this, all right. So, okay. So, this is how it looks like. So, this is the value it takes at 1 and this is FMB, okay. And you can also very clearly see that if I increase the temperature, the tendency of the system will be to fill higher energy states, right. So, if I increase the temperature, which is with the red color, so this curve will become something like this, okay. So, it will shift to the higher energy values and it will become lower in the low energy values. So, if I increase temperature further, so this is what this curve becomes, okay. So, basically here if I call this as temperature T1, this is T2 with red and T3 with yellow. So, here what we have is T3 is greater than T2 and is greater than T1, okay. So, the distribution shifts towards the higher energy values as we increase the temperature, okay. Okay, so that was the Maxwell-Boltzmann statistics, which is classical and distinguishable. Okay, so let us now look at the Fermi-Dirac. Okay, or let's do for Bose-Einstein first. Let us now do Fermi-Dirac. Okay, so in Fermi-Dirac we have f of ft equals 1 divided by e raised to the power epsilon minus mu by kBt plus 1. Okay. And again we can take the first simple case where epsilon equals mu, that implies your Fermi-Dirac the occupation index basically becomes 1 by 2. Okay. So at epsilon equals mu, so I'll plot that again. Okay. So this is your epsilon axis, this is your mu, and this is your f. Okay. So what we are saying is that mu, so the value of this distribution is half. Okay. So this is 1 by 2, and say this is 1 somewhere here. Okay. Okay, so but for epsilon greater than mu, we can check that fd is less than 1. Okay, so in this side this function is less than half, and for epsilon less than mu, fd is greater than half. Okay, in fact this should be less than half. Okay, and also for epsilon less than mu at low T. Okay, so if we take temperature almost equal to 0, if I put here, so this quantity will become very close to 0. Okay, my f of fd will almost take the value 1. All right, so let us now try to plot this. Okay, so what we have seen is, so for epsilon equals mu, this value takes this distribution takes the value half. Let me draw this dotted lines here. Okay. So but when epsilon is much smaller than mu at low T, this almost takes the value 1. Okay. So these are the extreme values. So when epsilon equals mu, it passes through half and then it goes to something like this. Okay. So this is how this distribution looks like. It doesn't diverge like Maxwell-Boltzmann, but it achieves a value 1 when epsilon is much smaller than mu. Okay. And you can also see that if I now lower the temperature, in fact if I take the limit where temperature goes to 0, for all the energy values which are lower than this chemical potential, the Fermi-Dirac, this occupation index will take the value 1. Okay. So basically if I draw the blue line which corresponds to temperature 0, so this is exactly 0, this is how it will look like. Okay. It basically becomes a step function. Okay. So this is T equal to 0. But if I increase my temperature, okay, so the black line is T greater than 0, so this is T greater than 0, and if I increase my temperature further, so we can see that it still passes through half. This is how it should look like. Okay, so this is how it looks like, and this is okay. Again, I can do that. So this is T0. So I can call this T1, and the yellow one I can call as T2. Okay, so here my T2 is greater than T1, and of course this blue one is 0. Okay, so T is 0. So this is how this distribution looks like, and this basically just tells you that as we increase the temperature, okay, so we'll say we start with T equal to 0. So all the particles, they are occupying energy levels which are below the chemical potential. Okay, so there is no occupation beyond this. But as we start increasing the temperature, the particles start hopping into the higher energy states, and that population increases as we increase the temperature slowly. Okay. So that is Fermi-Dirac statistics for you, and let us now look at the Bose-Einstein. Okay. And here we saw that f of Bose-Einstein is 1 divided by e raised to the power epsilon minus mu by kBT minus 1. Okay. So, this is minus. Okay. So, now let us try to understand this. Okay. So, again here you can see the first thing. So, for epsilon equals mu. So, for energy levels which are equal to the chemical potential, so this term basically becomes 1, and 1 divided by 1 minus 1 is infinity, right. So, f of Bose-Einstein, that goes towards infinity. So, it diverges essentially, right. And but however, for epsilon less than mu, epsilon greater than mu, so f of BE becomes finite, okay, and it progressively decreases, right. And epsilon can't be less than mu because the particles are already occupied in this energy state, right. So, if I now plot it, so this is how it looks like. Okay. So, this is our mu, this is our f of Bose-Einstein. Okay. So, let me draw this dotted line. So, what we see that what we saw that this diverges as epsilon becomes mu. Okay. So, this is how it looks like. Okay. So, it is a strongly diverging function, okay, something like that. So, this is strongly diverging function. So, it basically goes to infinity at epsilon equals mu. So, this is epsilon axis. And again you can check that as I increase my temperature, so higher and higher energy states will be occupied, right. So, this basically will shift towards higher energy states, all right. So, basically if I increase my temperature, so this will basically move like this, okay. And while, okay, maybe I can, okay. So, essentially these curves diverge. Okay. So, this is diverging, the yellow is also diverging, okay, and the blue is also diverging. Okay. So, it is diverging at epsilon equals mu. Okay. So, this is mu. So, this becomes so multiple occupancy. And this is essentially the consequence of bosons having integer spins, that they do not really obey Pauli's exclusion principle, and as the energy goes to this free energy, this chemical potential, so all the particles, they can have the same quantum state, right. So, they can exist in same quantum state. So, we have infinite occupancy, right. And in fact, this statistics has profound consequences upon some of the properties that we know, which are like superconductivity or superfluidity. Okay. So, these statistics play essential role, basically the defining role in giving rise to these anomalous properties like superconductivity and superfluidity. Okay. So, therefore, essentially to summarize our statistics that we have learnt, so what I can do finally, I can plot all of them in the same graph. Okay. So, we have this f, we have this energy, so there is this chemical potential mu, and say this is 1, this is 0.5. Okay. So, what we have seen so far is okay. So, let me, okay. So, for Fermi Dirac, which is blue line, so it passes through 0.5, okay, and then progressively decays. Okay. But for Bose-Einstein statistics, it diverges at epsilon equals mu, like red line. Okay. And for Maxwell-Boltzmann, which is yellow, it passes through 1 and it decays like this. Okay. So, basically this is Bose-Einstein, the yellow one is Maxwell-Boltzmann, and the blue one is Fermi-Dirac. Okay. And we can very easily see that for all values of temperature or for all values of energy, the occupation index in Bose-Einstein is always greater than occupation index in Maxwell-Boltzmann, which is always greater than occupation index in Fermi-Dirac. Okay. And this is because in Fermi-Dirac we have Pauli's exclusion principle, more than one particle can't have the same quantum state. In Maxwell-Boltzmann there is no such condition. However, for Bose-Einstein all the particles can occupy the same energy state. Okay. And there are few more terminologies or few more terms. So, if our occupation index for quantum particles which are fermions or bosons is much greater than 1, basically if we are somewhere here, okay, this is known as strongly degenerate state. Okay. If our F is almost equal to 1, this is known as weakly degenerate. And if our F is much smaller than 1, this is known as non-degenerate. And you can see that at higher temperatures where higher energy levels are occupied, so all the statistics they basically converge towards the classical statistics, right. So, if your temperature is very high, your densities are very low, like the chemical potential is very low with respect to your energies, all the statistics they basically converge to the classical statistics, which is Maxwell-Boltzmann. Okay. So, maybe I can write as T increases, so FBE becomes equal to almost equal to FT and becomes MB. Okay. So, all the statistics they converge. Okay. So, now let us basically look at the applications. Okay. Let us apply these statistics to basically get some results. All right. So, the first thing that we will do is we will derive so Maxwell's speed distribution from MB statistics, Maxwell-Boltzmann statistics. Okay. So, we saw that for Maxwell-Boltzmann statistics, so for MB, so the occupation index Ni by Gi was given by N divided by Z e raised to the power minus beta epsilon I. Okay. So, this was one of the results, and where Z is the partition function. Okay. So, or what I can also write it as, so I can write Ni equals Gi N by Z e raised to the power minus beta epsilon I. Okay. And this equation is for very discrete picture, where we have discrete values of cells and discrete energy values, right. But we can now convert it into more continuous case, right. So, for continuous energy values or energy states, I can just rewrite my Ni to be N epsilon d epsilon, where N epsilon d epsilon is the number of particles, right, and this is the density. So, this becomes G epsilon times d epsilon, which is now the degeneracy in some sense, right, times N by Z e raised to the power minus beta epsilon. Okay. So, I have just replaced these discrete values with uniform variation. All right. Now, what is epsilon, right? So, epsilon for an ideal gas is basically its momentum squared divided by 2m, right. So, this is the kinetic energy. So, from here we can see my d epsilon is basically p by m dp. Okay. So, I can now substitute for d epsilon on both sides, right. So, therefore, I can rewrite this in terms of p. So, d epsilon np times d epsilon, which is p by m times dp, that becomes g epsilon gp. Okay. Now, everything can be rewritten in terms of p times n by z e raised to the power minus beta p squared by 2m, and d epsilon is p by m dp. Okay, and you can see p by m cancels out, and this basically becomes np equals gp times, and by partition function e raised to the power minus beta p squared divided by 2m dp, and there is dp here as well. Okay, so this is np dp. Okay, and you have to just basically see this, right. So what is gp dp? That is the number of states between at momentum p within a tiny window of dp, right. Right. So basically gp dp is number of cells in in phase space, right, at p between p and p plus dp. Okay. And again going back to the definition, basically the way we discretized our phase space. So this is nothing but equal to triple integral in space dx dy dz times triple integral in the momentum space dpx dpy dpz, and to discretize all this we use the Planck's constant, which is divided by h cube, right. And this first triple integral basically just gives you the volume in real space times, so what is this triple integral? Now if you visualize it, so we are so since everything is radially symmetric, so we have a sphere of radius p, and we are taking another sphere of radius p plus dp, right. So this is dp, so this width is dp, right. So what is the volume of this thin shell of thickness dp? That is basically surface area 4 pi p squared times that thickness, right. So times dp. Okay, so that is exactly what this is, right. So this is v times 4 pi p squared dp and divided by h cube to discretize it. Okay. So we will basically substitute for this, right. So therefore we get np dp, and if I put it back here, so this is 4 pi p squared times the volume in real space times number of particles divided by h cube divided by z e raised to the power minus beta p squared by 2m. Okay, so this is what we have. Okay, times dp. Okay. Now what is our momentum, right? So momentum p is essentially m times v, where v is the velocity, right? So this implies, okay, so I am just doing little bit of algebra here. So p squared is m squared v squared, which implies my p squared dp is m squared v squared dp, and what is dp from here? So from here dp is m dv, right. So if I substitute for m dp here, it becomes m cube v squared dv. All right. So if I substitute all these values back into this equation, and also remember z was v by h cubed times 2 pi m kBt raised to the power 3 by 2. Okay, and this is for single gas molecule. So remember, we are interested in distribution of one gas molecule in an ideal gas over time, right. Okay. Now if we put all these values back into this equation, so substitute for z, substitute for p squared times dp from here, and rewriting p squared as m squared v squared. So you can check that we basically get nv dv. Okay, so this is the number of particles moving with speed v within a given window dv. So that basically becomes 4 pi V m cubed V squared, I am just substituting all those values here, times n divided by h cube times volume V by h cube 2 pi m kBT raised to the power 3 by 2. So, this is substituting for z times e raised to the power minus beta m squared V squared divided by 2 m times dV. Okay. And you can see there are various factors which cancel out. Okay. If you do this little bit of algebra, so I can write down the final result. So, NV dV takes the final form which is as follows. So, which is 4 pi n times m divided by 2 pi kBT raised to the power 3 by 2 V squared e raised to the power minus mv squared by 2 kBT. Okay, I am just rewriting beta as kBT times dV, and this is the final result. Okay. So, this is the Maxwell speed distribution. Of a gas molecule, of an ideal gas molecule. And you can see that this result is equivalent to what we obtained in. So, basically same result, same as obtained in our very early classes when we were looking at kinetic theory. Okay. So, basically what we have done is we have used the Maxwell-Boltzmann statistics to derive the Maxwell speed distribution of a gas molecule in an ideal gas. Okay. So, I will end here, and now I will end here. So, in the coming classes we will now apply the other quantum statistics to basically solve the problems on quantum systems. Okay. Thank you so much.